स्वागत है आप सभी का हमारे YouTube चैनल में जहां पे आज हम देखने वाले हैं कंट्रोल सिस्टम प्रैक्टिकल एनालिसिस ऑफ फर्स्ट एंड सेकंड ऑर्डर सिस्टम एंड डैम्पिंग फैक्टर आउटलाइन of this particular practical. First we discuss first order system, then analysis for step input, then concept of time constant, damping, damping factor, and second order control system, then relationship between damping factor and pole location. The first analysis of first order system for step input. So there is a consider one figure that indicate first order system with R of S and C of S as a function of 1 upon Ts with a negative unity feedback system. So G of S equal to 1 upon Ts and H of S equal to 1. So C of S divided by R of S, that is equivalent to G upon 1 plus Gs, that is equal to 1 upon Ts divided by 1 plus 1 upon Ts, and that is equivalent to 1 upon 1 plus Ts. So for step input, R of t is equal to U of t when t greater than 0, otherwise it is value is 0. So taking Laplace transform of R U of t, that is the 1 upon S. So here first we discuss that C of S divided by R of S, that is equal to 1 upon 1 plus Ts. So in that case, when input is a step, so R of S equal to 1 by S. So put this value in this particular equation. So C of S equal to 1 upon 1 plus Ts into R of S. So that is equal to 1 upon 1 plus Ts into 1 by S. Using partial fraction, so C of S equal to A divided by S plus B upon S plus 1 by T. So in this case, after solving A and B, so A equal to 1 and B equal to minus 1. So we get C of S equal to 1 upon S minus 1 upon S plus 1 by T. Taking inverse Laplace transform, C of t, that is equal to L inverse C of S, and that is equal to L inverse 1 by S minus L inverse of 1 upon S plus 1t. So it's equivalent to C of t equal to 1 minus e raised to 1 minus t by tau. So time constant. The value of C of t equal to 1 only at t equal to infinite. So you can see when t is equal to infinite, so 1 minus e raised to 1 minus infinite is equivalent to 0. So C of t equal to 1 only at t equal to infinite. Practically, the value of C of t is within 5% of final value at t equal to 3t and within 2% at 4t equal to 4t. In practice, t equal to 3t and 4t may be taken as steady state, and how quickly the value reaches steady state is function of the time constant of the system. Hence, smaller t indicates quicker response. Damping. Every system has a tendency to oppose the oscillation behavior of the system, which is known as the damping. Damping factor. The damping in any system is measured by a factor or ratio which is known as the damping ratio, and it is denoted by zeta. Analysis of second order system for step input. So here consider the second order system as shown in earlier case, it is 1 upon Ts. In this case, omega n squared divided by S into S plus 2 zeta omega n with same unity negative feedback. So here G of S equal to omega n squared divided by S into S plus 2 zeta omega n and H of S equal to 1. So C of S divided by R of S equal to G upon 1 plus GH. So when we put the G of S value and H of S value in this particular equation, we got omega n squared divided by S squared plus 2 zeta omega n S plus omega n squared. So this is the standard form of the closed loop transfer function, and these poles of transfer function are given by S squared denominator part equal to 0 indicate the pole. So S squared plus 2 zeta omega n S plus omega n squared equal to 0, and therefore S equal to as per the roots minus 2 zeta omega n plus or minus under root of 2 zeta omega n square minus 4 zeta omega n square divided by 2. So that is equivalent to minus zeta omega n plus or minus zeta omega n square minus omega n square, and that is equivalent to minus zeta omega n plus or minus omega under root of zeta square minus 1. So the poles are real and unequal if zeta square minus 1 greater than 0. So in this case, if zeta square minus greater than 0, so values are positive. So that is real and unequal. Like if zeta greater than 1, they lie on the real axis and distinct. Real and equal if zeta square minus 1 equal to 0. So in this equation, if zeta square minus 1 equal to 0, then both are real and equal. Then complex. If this part under root of zeta square minus 1 is less than 0, then poles are in second and third quadrant like zeta less than 1. So the poles are complex. Now, a relation between zeta and pole location, like if zeta value is between 0 and 1, they indicate under damped system. This is the pole location of zeta, indicated with the cross mark, and its equal step response indicate the under damped system. Then relation between zeta and pole location for zeta equal to 1. So when zeta equal to 1, it indicates critically damped. So this is the pole location when s equal to -1, and it is the step response in the case of critical damped system. Then next zeta greater than 1. With zeta greater than 1 indicate the overdamped system, which is the pole location of in the S domain, and it is a step response in the T domain. Now last is if zeta equal to 0, indicate undamped systems. In this case, the pole location in the imaginary axis, and this is the step response in time domain C of T. Now we have to solve next below example with the help of Scilab. So given that find which of the following system overdamped, underdamped, critically damped, and undamped, and plot the result. So what is the given value, like P of 1f is equal to s square plus 9s plus 9. Second is s square plus 2s plus 9. Third is s square plus 9. In this case, 2 zeta omega n is equal to 0. So zeta in this case 2 zeta omega n is equal to 9s. In this case, second case 2 zeta omega n is equal to 2s. And last case 2 zeta omega n is equal to 6s. So we have to find which system are there, P1, P2, P3, and P4, and we have to plot the particular system with the help of Scilab. Let's do with the help of Scilab. First CLC for clear screen, then variable it is, and define time sample from 0 to 15 in the range of 0.1. Sample of time from 0 to 15 in the range of 0.01. And second, define as equal to percentage as the alternative using as equal to poly 0 comma s. Then omega n square, that is equal to 9. Here given last one. So the first equation, P1 equal to s square plus 9s plus 9, or we can also write omega n square. So that is equivalent to s square plus 2 into zeta into omega n into s plus omega n square. So here compare with equation value, and we get theta equal to, like here, 2 zeta omega n like capital set for easy, omega n omega s square 2 zeta omega n. So omega n is 3. So 3 here, if 3 is there in this case, then 2 into 6s, so zeta is equal to 1.5. So zeta is 1.5. So when zeta is 1.5 in this case, so that means the system is overdamped or underdamped. So let's check the system. The system when theta is greater than 1, it's known as under overdamped system. So we define a system is overdamped system equal to system linear function of continuous time with omega n square divided by p1. So this is the linear system function. Linear system function. Then its response y1 equal to yes I am, and its step response with respect to t and overdamped system. Overdamped system. This is the simulation of time response of linear system. Now we draw the plot with the help of subplot. Subplot 2 to 1. So it indicate plot M and P, where M is the M indicate M by N matrix of of sub windows, and select with sub window with sub window. That means here 2 by 2 matrix sub window with first sub window. So that plot shown in the first part, and plot with t comma y1 with say color black. So black. So this is the plotting of overdam system. The title title is overdam system. Is the title of the plot. Title of the plot. Let's save this program and run this. Execute this. When we click here, we can see this is the overdam system nature that we have what earlier see in the presentation. Similar kind of result we can get with the help of Scilab. Okay. So this is for the overdam system. Now second example for the underdam system. So in this case, all things are same, like but we have to change the functions. So like just we have copy this, and p2 is change. So what is the p2? P2 is s square plus 2s. You get to just p2. P2 is s square plus 2s plus 9. So s square plus 2 zeta omega n plus omega n square. In this case, we can compare with 2 zeta omega n, and we get a is equal to 1 by 3. This is a 1 by 3, so zeta is less than 1, known as a underdamped system. So this is a underdamped system. Then omega n square divided by p2. Then system step T. This is the underdamped system. So underdamped system. Then the subplot of 2 to 2. Second part. Now second plot draw with the red color, so we can change the color with red. title is under damp system. Okay, so plot is drawn in the second part of the graph. Let's run this program. So execute, and we can see first one is over dam, second is a under dam system when zeta is less than 1. Okay, now third part is, let's copy the system. In this particular system, equation is changed P3 to s square plus 9. So theta is 0. So s square plus 9. So in this case, theta is equal to 0. So when theta is equal to 0, then it is known as undamped system. So undamped system. So in this case, W square divided by P3. This is the undamped system. So let's change it. Undamped systems. Now in third index or 2, 2, 3. We can also write like this: 2, 2, 3. Both are same. Now okay. Y1, this is Y2, this is Y3. Removing the confusion. So this is Y3, this is Y2. Okay. So P3, Y3. Now color is changed from red to green. So here I have to write green. Okay. And title is undamped system. So undamped system. Okay, this is the title of the plot. So this is for the undamped system when zeta is equal to 0, 2 zeta omega n. So 2 zeta omega n is term is absent in this particular P3 case. So let's run this program. Run this, and we check the result in the graph. You can see undamped system, green color. So when theta is equal to 0, this kind of nature is there in the Scilab operation also. So this is the undamped system. Now last case, that is about P4 when zeta is equal to 1. So once again we copy this, Control V. So in this case plus 6 into s, 6 into s. So s square, this is P4. S square will be minus compared with the equation value, and we get theta equal to 1. So this is known as a critical dam system. So it is critical dam system. So omega squared divided by P4, then step y4, this critical dam system, and fourth part. This is the fourth part, and this is y4, and this is a color of blue. So that's actually blue, and this critical dam system. That is the critical dam system. This is the critical dam system, fourth part, because theta is equal to 1. Let's run this program. So execute this, and we can see in the graph P4, 4 blue critical dam system. Is there any kind of error? Is there? Okay, there is one error in the critical dam definition. The critical dam system, critical dam system. I think okay. Let's run this program. Okay, so when zeta is equal to 1, so in this case, this is a critical dam system. This is the 4 figure that represent 4 different case of zeta. Like first one is a over dam system, then there is the under dam system, and this is a undam system when zeta equal to 0, and this is the critical dam system when zeta equal to 1. Hope you like this video. If any query is there, comment in the comment section.